Okay, in this video we're looking at multiplying matrices, but before we dive into it, we're going to look at this example here. So if we were given 4 houses in a sporting competition with different numbers of people in each position on the podium, first, second, and third, and we know that every person that placed first got 5 points for their team, every person that placed second got 3 points for their team, and every person that placed third got 1 point for their team. If we wanted to calculate the total number of points for each house, we want to take 60 and multiply it by 5, then add 63 times 3, and add 51 times 1. And what we can sort of see here is that it would be really useful if we could do this in a single algorithm that multiplied all of these numbers of positions by all of these point scores and just spat out the answer, what is all of their totals. And so matrix multiplication was developed to do just that. So what I would do is I would set up, well, first of all, let's just do it without the knowledge of matrices. So we'll brute force it. For Hamilton, we've got 60 times 5 plus 63 times 3 plus 51 times 1, which I believe is equal to 540. For Leslie, it's 71 times 5 plus 64 times 3 plus 74 times 1, which is equal to 621. Then for Barnes, we've got 64 times 5 plus 69 times 3 plus 71 times 1, which is equal to 598. And lastly, for Cunningham, we've got 69 times 5 plus 72 times 3 plus 68 times 1, which is equal to 629. So we can see that Cunningham is our winner. But that took a lot of brute force to do. And if we increase the number of houses or increase the number of positions, we can see that's going to get really time consuming really quickly. So instead, we represent it as a matrix that's 3 by 4. So 60, 63, 51, 71, 64, 74. Oh, sorry, 4 by 3, not 3 by 4. Okay, and then that just gets multiplied by a row matrix, 5, 3, 1. And so we multiply each each row by each column of this equation. So we do 5 times 60 plus 3 times 51 times, plus 51 times 1. Now that I'm thinking about this, I think this should be a column matrix. Does that seem right? Yes. So that would then give us a matrix that's 4 high that has our answer. So you could plug that into your calculator and it could calculate it for you. So it's handy to have this notation to sort of make the arithmetic of this a lot quicker. So let's look at the general case. If A is of order m times n and B is of order n times p, then A times B exists and its order is, well, let's look at this example. Our order ended up being 1 by 4, and so it ends up being order m by p. The number of columns in the first matrix must equal the number of rows in the second matrix, otherwise matrix multiplication is not defined. The product is obtained by multiplying each element in each row of the first matrix by the corresponding elements of each column in the second matrix. So, example 5. Let's take a look at writing down the order of each of these matrices. So, our first matrix, capital A, is 2 by 3, because we've got 2 rows and 3 columns. B is 3 by 2. C is 1 by 3. And D is 2 by 2. So, which of these products exists? So, I is A times B, which is 2 by 3 by 3 by 2. And we can see that yes, those line up. So we get, this is a product that exists, and it's going to give us, we'll also do part C in this as well, that's going to give us a 2 by 2 matrix. For part II, we've got 3 by 2 by 2 by 3. And again, we get that the 2's line up, so this does in fact line up as well. And that's going to give us a 3 by 3. Okay, so for part III, we've got 3 by 2, it's b squared, so it's going to be 3 by 2 by 3 by 2, which does not line up, so that product does not exist. We then have AC, so A times C is going to be 2 by 3 by 1 by 3. Again, these two don't line up, so our product doesn't exist. And lastly, we've got d cubed. So for d cubed, it's the same as d squared times d. So d squared gives us 2 by 2 by 2 by 2, which does exist and is also 2 by 2. And so if we multiply that by another 2 by 2, that also exists, and it's still 2 by 2. So let's calculate those three products that did exist. So I, and then V. So for I, we've got A times B, which is equal to 1, 2, 3, 4, 5, 6 times 2, negative 1, 0, 4, 5, 3. So that is going to give us a 2 by 2 matrix. And it's going to be 1 times 2. So 1 times 2 is 2, plus 2 times 0 is 0, plus 3 times 5 is 15. So what I'm doing there is multiplying each column by the row of the right matrix. Let's see that again. So for this entry here, I'd have 4 times 2 plus 5 times 0 plus 6 times 5. So that's going to be 8 plus 0 plus 30. For this next entry, I'm now looking at my first row and my second column of my second matrix. So that's going to be negative 1 plus 8 plus 9. And lastly, we're going to have negative 4 plus 20 plus 18. So computing all those sums together, I get the matrix 17, 15, 38, and 34. Okay, I was B times A. So B times A is going to give us a 3 by 3 matrix this time. So that is 2, 0, 5, negative 1, 4, 3, multiplied by 1, 2, 3, 4, 5, 6. Okay, and we're going to compute this a little bit more quickly now. So I would have in this first entry here 2 times 1 plus negative 1 times 4. So 2 take 4 is negative 2. We get 4 take 5 is negative 1. And we get 2 times 3 is 6, take 6 is 0. We get 0 times 1 is 0, plus 4 times 4 is 16. We get 0 times 2 is 0, plus 4 times 5 is 20. 0 times 3 is 0, plus 4 times 6 is 24. And then lastly, we get 5 times 1 is 5, plus 12 is 17. And then 5 times 2 is 10, plus 15 is 25. And lastly, 5 times 3 is 15, plus 18 is 33. Okay, I've run out of room here, but we'll just do part V over here, which is d cubed. Now, I'm going to split that up into d squared and d. So to find d squared, we're first going to compute the following. That's positive. Okay, and so that is going to give us 1 times 1 is 1. Take 2 times take 1 is positive 3, so that's 1 plus 3 is 4. Have I done this right? Sorry, 1 times 1 is 1, negative 2 times negative 1 is positive 2, so this is 3. Okay, then we've got 1 times negative 2 is negative 2, take 6 is negative 8, negative 1 times 1 is negative 1, take 3 is negative 4, and then we get negative 1 times negative 2 is 2, plus 9 is 11. So to find d cubed, we're then going to take that 3, negative 8, negative 4, 11, and multiply it by 1, negative 2, negative 1, 3. Okay, and that is going to give us the following 11, negative 30, negative 15, and 41. So that's our answer for d cubed. So notice that for two matrices A and B, AB is not equal to BA. So matrix multiplication is not commutative. It's not like 2 times 3 is equal to 3 times 2. In this case, because we have different orders, different sizes, we cannot simply change them around. In fact, the only case in which they are commutative, I believe, is in this case over here, where you square a matrix. Because you could just obviously flip these two around. There is also one other circumstance in which matrix multiplication is commutative, which is when you multiply by the identity. So, multiplying by the identity. Let's do I times A first. So our identity, we use context to discover it's going to be a 2 by 2 because we need to line up orders. So 1, 0, 0, 1. And when I multiply this through, I'm going to get 1 times 2, take 0. Well, that's just 2, right? And then for the second one, I'm going to get 0 times negative 3. Oh, sorry, 1 times negative 3 plus 0 times 4. Well, that's just going to be negative 3. And then for this entry here, I'm going to get 0 times 2 plus 1 times negative 5. Well, that's just negative 5. And then for 0 times negative 3 plus 1 times, well, that's just 4. So what we have developed here is that if we multiply something by the identity, it keeps its identity. Oh, funny that. Maybe that's where the name comes from. Well, anyways, that's not what the question's asking us. It's wanting us to show that it's commutative. So let's take a look at AI now. So for AI, we're flipping around the order. So now we're doing 2, negative 3, negative 5, 4. And 1, 0, 0, 1. And we will find that, yes, indeed, we're going to get 2 times 1 plus 0. You know how this is going. We're going to get 2, negative 3, negative 5, 4. So not only is AI equal to IA, but it's actually equal to A. And look at that. That's been down the bottom there, under our noses for us to see. So AI equals IA equals A, where A and I are square matrices, and I is the multiplicative identity matrix. And that is the final example for this video. Thank you for watching.